Hello friends. Have you ever wondered why engineers trust smooth curves to model bridges, why physicists use clean equations to describe motion, or why computer graphics look so fluid? The answer often comes back to one family of functions, polynomials. They are the best behaved functions in all of calculus, and in this video we are going to prove exactly why that is. We will build up two big ideas, continuity and differentiability, show that every polynomial satisfies both everywhere on the real number line, and reveal the precise relationship between the two. By the end, you will have a solid, rigorous foundation you can use in every calculus course ahead. Let us start with the first big idea, continuity. Continuity means a function has no breaks, holes, or jumps. Formally, a function f is continuous at a point x equals a if three conditions hold. First, f of a must actually be defined. Second, the limit of f of x as x approaches a must exist. Third, that limit must equal f of a exactly. Now here is the key insight for polynomials. Take any polynomial p of x. Because polynomials are built only from addition, subtraction, and whole number powers of x, we can always evaluate them by direct substitution. Plugging x equals a gives a real number, the limit equals that same number, and all three conditions are satisfied automatically at every single real number a. No exceptions, no special cases. Next, let us look at what it means for a function to be differentiable. A function is differentiable at a point if its derivative exists there, meaning the slope is well defined at that point. The formal definition says f prime of x equals the limit, as h approaches 0 of f of x plus h, minus f of x, all divided by h. Let us apply this to a single term, x to the power of n. Expanding x plus h to the power of n with the binomial theorem, the leading difference gives n times x to the power of n minus 1 times h, plus higher order terms. Dividing by h and letting h approach 0, all remaining terms vanish. We are left with n times x to the power of n minus 1. That is the power rule. Since every polynomial is a finite sum of such terms, polynomials are differentiable everywhere. Next, let us see how differentiability and continuity connect. Here is a theorem every calculus student needs to know. If a function is differentiable at a point, then it must be continuous there. The logic is direct. For the derivative limit to exist, the function values must converge to a single finite number, which is exactly what continuity requires. But the reverse is not true. A function can be continuous at a point, without being differentiable there. The classic example is f of x equals the absolute value of x. It is continuous at x equals 0, no break or jump. But a sharp corner sits at the origin. The slope from the left is -1. The slope from the right is +1, so the derivative limit does not exist. Continuity and differentiability are related, but they are not the same thing. On to a concrete example. Let us make this concrete. Take the polynomial f of x equals x cubed minus 4x plus 2. We want to verify continuity at x equals 2 and confirm it is differentiable there. For continuity, we check the three conditions. F of 2 equals 2 cubed minus 4 times 2 plus 2, which gives 8 minus 8 plus 2 equals 2. The limit as x approaches 2 also equals 2 by direct substitution, and it matches f of 2. All three conditions hold. For differentiability, we apply the power rule. The derivative f prime of x equals 3 times x squared minus 4. At x equals 2, that gives 3 times 4 minus 4, which equals 8. The derivative exists and equals 8, the slope of the tangent line you see here. Both properties confirmed, exactly as the theory predicts. Now let us pull everything together. Let us bring it all together. Every polynomial is continuous at every real number, because direct substitution always satisfies the three-part definition. Every polynomial is differentiable at every real number, because the power rule, derived from the limit definition of the derivative, applies term by term across the whole function. And the bridge between the two is a one-way street. Differentiability always implies continuity, but continuity alone does not guarantee differentiability. Coming up, we will look at piecewise functions, where these properties are no longer automatic, and you have to check each piece carefully. That is where the real detective work begins. For now, pick any polynomial, choose a point, and verify both properties yourself. The practice will lock this in. Thanks for watching, and I will see you in the next one.